Okay, we will continue with what we have seen in the last class. So once a suitable value of value for P is selected, then that is to define the overall shape of the profile, the value of the friction coefficient corresponding to the beach slope can easily be obtained. There are several ways of getting this done. So you have to again go into the manual, coastal engineering manual or the shore protection manual to look into these aspects. So this is a figure which shows the variation of the longshore currents, that is the dimensionless longshore currents as a function of the dimensionless distance between the from the shore towards the sea. So you see that there are two values for the capital P, one is 0.1 and the other one is 0.4. And here you will see when you look at this picture, if the value of coefficient that is the friction coefficient that has been used in the solution to equation 2 here, this is the maximum velocity equation 2. Okay, if so the value of the current at x equal to, that is what, x equal to 0.5 will agree with the value obtained by equation 1 and 2, at least at the mid surf zone. We will come back to the mean velocity, maximum velocity, etc. later with the help of a few more slides. I will again explain this later. Now earlier what we had for a single wave, what did we do? For a single wave we calculated the PLS parameter, and then the PLS parameter is nothing but the driving force. Then we sort of equated it to the immersed weight of the sand. Remember, IL, PLS, IL, etc. Please recollect, go through the lectures again or the lecture material. So the same way only we are going to do for this. So what we do is, so those are for a representative wave height, which may be either the HRMS or the HS or just the monochromatic wave of wave height. Okay. So the other way of doing this calculation of the sediment transport, once you know that the sand transport is within the surf zone, so we can integrate this whole thing to get the total sediment transport. Okay. So once you know the, for which you know, you should know the distribution of sediment transport rate. Once you know the sediment transport rate, you integrate and get the total sediment transport rate. Okay. So such figure can be drawn for every month. Okay. For a constant, for an average breaker wave angle or average breaking wave characteristics for each of the month, and then try to integrate and get it. Okay. And then you can try to compare, one is by comparing the sediment transport rate by integrating the distribution of the sediments within the surf zone, or using the Circ formula, or maybe Komar formula, which we are discussing right now. Okay. Komar formula also is there. So you can use all these three methods and then you can also compare. Later I will just show you some of the typical examples where we have used all these formulas for predicting the sediment transport rate, maybe one of the coast, stretch of the coast along Indian coast. Okay. So some maybe Kerala or Chennai or so the distribution of sediment transport across the surf zone is obtained using the methodology suggested by Komar. What it gives a local sand transport produced by waves and longshore currents. So this is IL is, this is what he obtained an expression which is going to be a function of this longshore current velocity, which is going to be the driving force. Okay. This expression is calling it as local sand transport due to waves and the longshore currents. Now here the different variables are given, are mentioned here. F is the drag coefficient, d and v are the local depth and the Longshore current velocity, which are the functions of the distance from the surf zone. The distribution of v as a function of x we have already seen earlier, right. So you remember we were it involved a number of parameters like p1, p2 etc, a etc, the one what we have seen yesterday, and k2 is a proportionality constant between the available power and the resulting transport, which was similar to what we had done earlier under the energy flux method. Okay. So unlike the solution to the Longshore current velocity, equation 2 gives the maximum current velocity, okay, maximum current velocity, which can be used to obtain currents even beyond the surface width. The solution of the transport rate that is given in the earlier equation, this equation, is valid only up to the width of the surf zone, because as we have seen the Longshore current velocity, that is v by v naught, we drew for example this was maybe this is the surf width for example, this is what we had, and then we had here, remember yesterday we have seen, right, and but then I said that this equation can go beyond the breaker zone, right, but here, so although the current velocity is there, but the equation 4 is valid only up to the within the width of the surf zone, you understood, because this is where the dominance of the sand takes place, and that is why you are trying to equate the power and the sand in order to get the total quantity by integrating. So according to Kumar and Inman, the total immersed weight now can be expressed, this is using the wave characteristics, okay. So similar, more or less similar to what we have done under the energy flux method. So now the coefficient k, so we have one equation for the local sand transport, and then this is for the total immersed weight of the sand. So these two when you equate, then you have a coefficient that needs to be evaluated, and that coefficient is k2 is integrated. How do you get that k2? You can get k2 by integrating, here the velocity is going to vary within the surf zone, okay. So you need to integrate that across the surf width and equating it to the total immersed weight. So you integrate the total, integrate the sand distributed in this, and this has to be equated to the total immersed weight, you understood, this is the total immersed weight, and then once you do that, then you get the proportionality constant also. So the dance, and also you can also with this help, with the help of this, you can draw the distribution within the surf zone. What we will do is we will try to use some of these informations. I am not going to go into the complete details, but I will try to demonstrate how you use some of these equations and expressions, and in order to arrive at least the Longshore current velocity, and maybe if time permits the sediment transport rate. So what all we have seen? We have seen maximum velocity, then mid surf velocity, then now we are having another velocity which is Vb. So the radiation stress of Langevin, he came up with so all these equations do not get bogged down, because of we are involved, because the topic involves so many formulas. Some of these formulas will be allowed to be brought for the examination, okay. But what I want you to do is look at the problems, the application of the formulas, that is much more important. Where do you apply and when do you apply? So here a small m, m1, this should be small m, and here m1, m is the beach slope, capital M is given as given by the expression there, where this is the mixing coefficient, which I have already explained yesterday what is meant by mixing coefficient, and that is going to be between 0.17 to 0.5, that is 0.17 for little mixing and 0.5 for complete mixing, but the commonly they use a value for about 0.2. Okay. So you see a number of coefficients are involved when you are dealing with sediment transfer, so it is becoming more and more complicated and more so we use the word estimates. It is not so easy to accurately calculate the sediment transport whatever is involved in the field of sediment transport. So the other things are the friction factor, and friction factor is taken as 0.01, and beta is you know that is nothing but the breaker index, that is 1.2. Okay. So applying equation 6, that is this particular equation, which is the velocity, the Longshore current velocity at the breaker line, when this was applied to two sets of data, then it yielded predictions that was that the average was about 0.3 of the measured values. You understand? So then so in part these predicted speeds were found to be much lower than Vb, that is what than that predicted by this equation. The measured was less, so that means there is a velocity which is much less than the velocity at the breaker zone. Is that clear? And that could be, so therefore the equation 2 was multiplied by a factor of 2.3. This was done by Longitude-Higgins equation to get us what is called, what is defined as the mean Longshore current velocity. So we have yet another factor which is V bar. Okay. So we deal with maximum current velocity, mid-surf current velocity, velocity current velocity at the breaker zone, and then we have the mean current velocity within the surf zone. So now you please recollect how many kinds of velocities we are dealing. Earlier so we had celerity, group celerity, orbital velocity, mass transport velocity. Okay. In fact, we have rip current velocity, which we have not gone into the details. Now under the near shore fields you have so many other kinds of description of the velocities which are being used in the near shore dynamics. So Longshore current velocity are more sensitive to changes in breaker angle and to a less degree to the changes in the breaker height. So that is why this you can try to work out. You have the expressions for the Longshore current velocity. Try to keep your breaker wave height constant, keep changing your breaker angle by a certain percentage, maybe for 2 or 3% or maybe 5%, and then you repeat the same thing by keeping the angle same and then changing the percentage of the wave height. You will see that the change in the percentage in the angle will really change, result in a significant change in the Longshore current velocity. That is true, no? Because the Longshore current velocity, as I have said, it is because of the oblique wave oblique attack of the waves. Okay. So more is the angle, greater will be the Longshore current velocity. Again to recollect, so when you stand here and look into the ocean, if you see that the waves are at a particular location is approaching normal to the shore, that means what does it mean? You do not have a Longshore current velocity at all. So in such a location, if you have some kind of a vertical an obstruction normal to the cylinder, normal to the shoreline, the changes will not be appreciable. Now go to an area where you have only this much of angle, and you have having a, so this indicates that there is a Longshore current velocity. Now what is the kind of variation you may have? You may have the deposition or the advancement, and you may have, not you may, you are bound to have this kind. Is that clear? Suppose if this angle is more, I am keeping your h constant, I am changing only the angle. So now if the angle is more, then the deposition will be more, and similarly the erosion can also be more. So this is the physical significance of the importance of evaluation of the, or knowing the, having a knowledge on the variation in the Longshore current velocity and also the variation in the wave directions, particularly in the near shore. So however the volumetric rate of flow of the longshore to the breaker height is proportional to h square, that is what it says, the formulas, everything. So I am sure that this is understood, right. Finally, in addition to the above, we have a number of formulae that has been proposed for the mean longshore current velocity. So what we could cover here is only a handful of what is supposed to be known to coastal engineers. If you are taking this as a field of specialization for your future, I suggest you read a number of books, references that are given in the lecture material. Okay. Now we will, having gained some knowledge, I hope things are clear, we will just go on to some of the problems related to longshore current velocity. So here we are given the data month wise. So maybe your wave height, deep water wave height is 1.5 meters, wave period is 7 seconds, deep water wave direction is 50 degrees, then the beach slope is 1 in 9000. Calculate the average longshore current velocity and the longshore velocity at the breaker zone. So the procedure is, slope is also given. So if you want, you can use this equation which relates the deep water wave characteristics in order to obtain the value for the breaker wave height. All these data, these formulas are discussed in the chapter on wave deformation, and then this will yield you a value of 1.685 meters for the breaker wave height, and then thereafter you get the dB, that is the breaker depth, as 2.16 meters. Then get into the wave tables and then derive the value of the d by L corresponding to the d by L naught, and this will be the d by L for this particular dB, and then you will get the wavelength at the zone, in the zone of wave breaking. Is that clear? Is that clear? Clear? Okay. Then once that is known, you can calculate the breaker velocity using Snell's law. You can get the breaker angle. All these things have already been seen earlier. Now longshore current velocity at the breaker zone is given as shown here. So where m1 is the beach slope, which is 9 by 1000, then m1 is given by this. So you can use the factor as 0.2 for the mixing parameter, and all other parameters are known. Beta is 1.2, friction coefficient is taken as 0.01, and hence you can calculate this because the breaker angle has been evaluated, breaker height is given, and then this is the order of the velocity at the breaker zone. Is that clear? Then comes the mean longshore current velocity as derived by Langevin and using the radiation stress theory. So this is a simple equation which can be straight away used because m is the beach slope and all other parameters are known, and now this is what is you get, that is the mean longshore current velocity So the Longshore current velocity can vary something like this. Okay. So that is only a sample calculation which I have presented. Now this figure, this table shows the every month, January to December for a particular location. So all this h naught t and theta naught is supposed to be your input data, available data, for which you are supposed to calculate all this these two parameters, that is the velocity at the breaker zone and the average velocity. So you calculate the same procedure, so this shows the variation of the breaker wave height, this shows the variation of the breaker depth for different months, the breaker wavelength, then breaker cellularity, deep water cellularity, breaker angle, then M1, which is going to be a constant in this case. In fact M1 can change also, because beach slope cannot be always same also. So we are assuming that it is the same. So we have got that 8.262, and then the variation of both the velocity are given here, which incorporates the direction of the velocity also. Okay, the velocity at the breaker zone as well as the average velocity. Is that clear? Now the calculation of PLS parameter, which is a very important parameter, because that is only after you calculate the PLS parameter can you really get the quantity of sediment transport rate. So for the calculation of PLS parameter, there are several formulas which we use in the wave deformation, as we have seen under the chapter wave deformation, for the for getting the breaking wave characteristics. Okay, because breaking wave characteristics are the characteristics which are going to control your variation of the PLS, thereby controlling the quantity of sediment transport. So here you have what I have listed are the formulas given by different authors, and then these are the different formulas. So you can sit and do the calculation by yourself. So you use the beach slope here is we have taken as 1 in 50, and then you calculate all those parameters that are needed for calculating your PLS. So for calculating your PLS you need the HB and your CB, and this is going to vary with the type of formula, the kind of which is the formula which we are going to use. So look at the variation of the breaker. So look at the variation of the breaker wave height. Breaker wave height is going to be controlled this way, and the breaker depth variation is given here. So you have a variation of about 1.97 or close to 2 to 2.2. So that is the kind of variation you can anticipate when you are trying to use different kinds of formulas. Okay, is that clear? But so this gives a clear view about the formula that can be used. So finally, having looked into the two problems on Longshore current velocity, we will just move on to, those are all current velocities for a particular month, maybe the average of the velocity at the breaking, average of the average velocity, okay, monthly average. So now what we are trying to do is we are trying to understand how the distribution of Longshore current velocity would look like. So as I have told you the principle, once you get the distribution of the Longshore current velocity, you can integrate and get the total sediment transport rate. That is, you have to equate it to the immersed volume of the total immersed volume of the sand. That is what we have already seen now. So if it is not so clear, please look into the lecture material and also the file which is available to you, that is the PDF files, so that things are more clear. So here 3 meter wave breaking wave with a wave period of about 11 seconds approaches a beach. Beach slope is given as 1:75, and at an angle, so the breaker angle itself is given here, okay, that is 5 degrees. Okay, so 5 degrees is nothing but it is a breaker angle, because it is mentioned as breaking wave height, breaking wave. So calculate the Longshot current velocity assuming that the friction factor may be taken as around 0.003 and the mixing parameter has 0.012. If these values are given, you can estimate all these parameters. So these are some of the formulas which we need to have. So we have the parameter A, then B1, B2, capital P and this one. So what are all the things which we need to calculate? First, as I have said earlier, yes, that is right, you have to calculate P. P is pi into m, that is n is already given to you as 0.012. So and so gamma is nothing but the breaker index, and then you can calculate Cf is also given, so you can calculate P. So now P is how much? P works out to you have other parameters like your P1, all these parameters need to be worked out. So first we will have the breaker index. So breaker index can be worked out as shown here, that is here for the present problem. So this is one of the method to use to get the breaker index. This is the in terms of beach slope is given to you, hence you use this method. So beach slope is 1/75, wave period is given, breaking wave height is given. So you use this to get the constants A and B, as we have got 9.79 and 0.8 for A and B respectively, and then B can be the gamma can be obtained as per this formula given here, and then that is going to be approximately 0.86. Is that clear? See, although we use 0.78, sometimes it depends, it varies anywhere between 0.78 and 0.82, 86, etc. 86 in fact is slightly on the higher side. Okay. So it is usually it varies between 0.78 and 0.882. So now you have once you have got your breaker index, then you can straight away get your breaker depth, because the breaker height is already known. So your breaker depth is equal to, breaker depth is 3.48 and breaker height is already given, so no problem. So slope is m is slope is 1:75. So you can get your, what is that? That is the surf width. Am I right? Are you following? So surf width is around 261 meters. Okay. Now what is epsilon? Epsilon is going to be, I will just run back and forth so that things are clear for you. So here epsilon will be equal to 1 divided, so in this equation this is already evaluated, so just you need to use this equation, and then that would give you epsilon equal to 0.785 and epsilon square, okay, that does not matter, and Fc is also given to you, no problem. So straight away you have to use your maximum velocity. How do you calculate the maximum velocity? This is the equation, we have already done one problem similar to this. In the first problem today was based on this. So use all these things, all these variables are already given to you, already known. So you get V naught is equal to 1.17 meter per second. Okay. Now the next task is to get the p value. P value is pi, m is known to you. So that is m is equal to 1 by 75, your n is 0.012 and then gamma is the breaker index and fc is equal to 0.003. Is that clear? So this is going to work out as 0.195. Is that clear? So next you have all these equations, you have evaluated this one is clear, this one is clear. Now the rest is going to be quite straightforward. So once you have the p and epsilon, then p1 will be equal to that expression which is going to give you 1.914 and p2 is going to be minus 3.4 and capital A is, once you calculate the p2 you can calculate A, that is going to be 1.62 and then you will next your b1 and b2. So you already have evaluated the xb, that is the surface width, as well as your velocity. What else you want? What else you want? So you have an expression which can be straight away used by using all this the values for all the different coefficients. Okay. So what I do is I take a capital X from 0.12, run all the way to 1.5 times the surface width. Okay, x by xb equal to 1 is exactly at the surface width, right. So that is what I have done here. So then distance from the shore is given here. So it starts from 26 meters going all the way to around 400 meters here for this particular problem. Then v by v naught you can calculate using this particular expression. So I would just so this is the equation, okay. This is the equation we are trying to, people who have not attended last class, please look into this. So this was the equation, it is quite straightforward, okay. So this is the equation where you have the top one as the expression for calculating the Longshot current velocity within the surf zone, and after the beyond the surf zone you use the this expression. So this is within the surf zone and this is outside the surf zone. Is that clear? So use this accordingly and then you will get the variation of the current velocity as given here, okay. So Longshot current velocity, so this is the dimensionless velocity. On the last column you are going to have the Longshot current velocity within the surf zone. So what you see is it increases and then close to the mid surf it is going to be about 0.5, you see that it is around 0.45 which is going to be the close to the maximum velocity, and you can also find out what is the average velocity in this case. So the mean velocity in this case would be approximately 0.26 meters per second, and this is going to be your distance from the shore to the Longshot current velocity within the surf zone. So it varies from about up to about 0.5 meters up to about 0.46 meters per second for this particular problem, and then it extends up to about, so what was the surf width? Surf width was 260 meters, right. So you see that beyond the surf width also you can have certain amount of Longshot current velocity, as you can see in this, okay. You still have certain amount of velocity being generated beyond the surf zone. Is that clear? Any of you have any doubts? So with this we have completed the Longshore current velocity and Longshore sediment transport. Any of you have any doubts?
Sir, what is meant by immersed weight of sand?
That is, what is the total weight that is immersed when it is immersed in the water, sea water?
That is moving as well as that is depositing.
That is also depositing. Okay. So when you look at the sediment transport rate, not only the calculation, the measurement is even more complicated. So when you want to measure the sediment transport rate in the field, it is quite difficult. Then how do you have some kind of estimates on the sediment transport rate? One way is to have a trap, which may not be accurate, but still it gives a guideline, it serves as a guideline. You have a sand trap, take a sand trap, it is not so easy, and all these things are estimates again. So when the sand is being collected over maybe 3 months or 4 months or 5 months, take the quantity of sand which has got filled up with the sand trap, within the sand trap, and that will give you to a certain extent what is the kind of sand transport which is taking place in the region. That is one way of doing it. The other way is to look at the approach trestles, approach channels. If there are some major ports, okay, approach channel, they have to keep on dredging in order to maintain certain depth for the vehicles, for the vessels. So using the dredging records, you can have an idea concerning the quantity of sediments moving in that location. Then the other way of looking at is satellite imageries. Now satellite images has come out recently, so you can use these imageries spread over a few years, superpose all those plots, all those imageries one and over each of these imageries, and that will give you some idea concerning what could be the sand transport. Is that clear? So these are all some of the ways of measuring the it is not accurate. Similarly, as I said earlier, when you want to do some experiments with understanding the movement of sand in the coastal zone, particularly in the coastal zone, again it becomes very complicated because modeling poses a big challenge. Earlier most of the projects were based on physical modeling, and once you see once the rapid growth in the computers took place, then people started resorting to numerical models. This is what I have told in the last class also. So it is quite a bit challenge, particularly this area. There are lots of coefficients, a host of parameters which you need to take care of, and it is not so easy. Okay. Anyway, the problems which we have worked out gives you a kind of a feeling to the nature of the problem, the magnitudes associated with the problem. So what could be the quantity of sand that can move? As I said, please remember, along the east coast of India we can have the quantity of sand that is moving towards north is to the tune of about 0.8 to 1 million meter cube per year. That is a huge sand quantity of sand, huge quantity of sand that is moving, and it is quite a big challenge handling this sand movement. Okay. So I am sure that now with the lecture on all the other aspects, we have seen some of the case studies earlier along, particularly along the Indian coast. Now based on that all those case studies, now we have also looked into the mathematical aspect of getting all those variables that is going to control the physical phenomena that is going to take place. Now you should try to link these two. I am sure now you have the answer why we have to study all these things and where do you apply all these things. Do not be worried about big long formulas. Long formulas can always, as I said earlier, you can bring the formulas, there is no problem. what matters is using the correct coefficient for the correct correct proportionality constants. There are so many proportionality constants, that is very important. Okay. So any other question you have? I think I can stop here unless you have any questions.